Good afternoon, everybody. Thank you for coming along this afternoon. It's my pleasure to introduce Dr. Robert Patterson, who's giving our seminar this afternoon. Rob has been, as many of you know, has been in our group for the last 4 years, doing his PhD in hot carrier solar cells. He's supported in this work by the Global Climate and Energy Project in Stanford University. Rob did his first degree at Queen's University in Kingston, Ontario, and then moved on to do his master's in physics at the University of Alberta, before joining us at UNSW in 2008. Rob did his PhD in hot carrier cells, and now he's working on a postdoc, again on hot carrier cells, and has recently won an Australian Solar Institute fellowship working on hot carrier solar cells and also other nanostructured solar cells. So thank you, Rob. I'd look forward to your presentation.
Okay, thank you very much, Gavin. Thanks for that. And thank you all for joining me this afternoon for a talk I'd like to give on some modeling of Phonon band structures for hot carrier solar cells. And so hot carrier solar cells are a novel third-generation photovoltaic concept which achieves high efficiency by minimizing thermalization loss. And thermalization loss in single-junction photovoltaics can be significant. And so that is one of the important loss mechanisms that we can try to address. So in order to address thermalization loss, it's good if we understand what a hot carrier is. A hot carrier is created when a photon with an energy much bigger than the band gap of the material is absorbed by a semiconductor. And when that happens, we have some charge carriers which are excited well above their respective band edges, well away from their respective band edges. And when these charge carriers have an opportunity to relax, they can do it in a few different ways. And the way we focused on to date has been through the emission of phonons. So this is called thermalization loss. Okay, so if we're going to address this loss mechanism, it's good to understand it in some detail. And so what I've drawn here are some band structure diagrams for electrons and phonons in a typical bulk material. And what these band structures allow us to do is chart the motion of particular quantum particles in terms of their energy and momentum. So we can look at things like decay processes. So the typical first creation of a hot carrier is the same as previously described, and the thermalization process is also the same. But in more detail, we can look at what happens with the phonons that are created in these thermalization events. And these phonons all have a particular character. They are low momentum, low K phonons, and they're high energy in bulk materials. So they sit here at the top of this energy and momentum diagram, this band structure diagram. And that would be just fine. These phonons couple strongly to electrons, except that decay processes can occur. And in bulk materials, typical decay process involves two lower energy phonons being emitted from a decay of this high energy phonon. And this is an energy loss mechanism because while these phonons couple strongly to electrons, these ones are considered not to couple strongly. And as a result, they diffuse through the material and give rise to heat. So in order to inhibit this process, the initial story is the same. However, I want to point out that this phonon band structure diagram here now has a gap in it. And if that gap is large enough, then there are no states available for the decay product phonons to go into, to first order at least, for 3 phonon processes. And if that's the case, then this decay is inhibited, and we have the opportunity for these phonons at some later time to be reabsorbed by the material and reheat charge carriers for extraction. Okay, so I just want to, oh no, what happened? Okay, I just want to emphasize that this is all a result in this approach. These long phonon lifetimes are a result of a large phonon band gap in the material. Okay, so now that we have some understanding of what thermalization loss and some detail is all about, we can start to think about engineering a device which addresses this loss mechanism. And I think a reasonably simple analogy can be taken in terms of a tank filled with hot particles, which is either well insulated or poorly insulated. Okay? And we'd like to make this tank as well insulated as we possibly can. So insulating in terms of electrons is not that difficult. We can imagine just introducing a barrier into the system. And that barrier is provided by energy selective contacts. And these energy selective contacts are typically resonant tunneling structures which have a very narrow bandpass for electrons. So they act kind of like a valve, only allowing certain energies of electrons to pass. So electrons stay within this absorber material, and in terms of our tank analogy, that means that these electrons can scatter with each other, and that's fine. That gives rise to a population with a distribution that looks like some kind of a statistical thermal distribution. Okay, that's just a renormalization of energy that doesn't necessarily incur any losses. But if these particles are able to scatter with the walls of the container, then that can potentially lead to some kind of energy transfer to the material that is holding the charge carriers. In this case, the semiconducting material, which is acting as the absorber. And if this can lead to thermalization loss, if these phonons, if this heat transfer does not stay within the system, then we can potentially lose energy. And we would, of course, like to reabsorb this energy at some later scattering event. So to insulate our tank against this thermalization loss, in this approach, again, we need large phonon band gaps in the absorber material so that these phonons which are created during scattering events are long-lived. So, having emphasized the importance of phonon band gaps, you can safely ask the question now, what kind of materials have large phonon band gaps? And indium nitride has been discussed at length in this context. It has a large phonon band gap shown here. And that is due to the large difference in atomic mass between indium and nitrogen, indium being much heavier than nitrogen is. Also, periodic modulations of bond stiffness or bond strength can give rise to phononic band gaps in materials as well. So that's great. At the UNSW, we have a project which is ongoing in terms of investigating indium nitride, but it was also of interest to ask the question, is there any potential for nanostructured materials to give us some advantages in terms of phononic properties? In particular, quantum dot superlattices. So to that end, to explore that question, I did some modeling work. And I just want to describe some of the basics of that modeling work at this point. If you have a material which has red atoms and blue atoms in it, two different types of atoms, the blue atom experiences a potential as a result of the red atom which looks something like a Lennard-Jones potential, which is what I've drawn here. To first order, at the minimum of this interatomic potential, you can expand the potential as being parabolic. That's the first non-zero order. It's the second order expansion coefficient is non-zero. And this is called the harmonic approximation. And what it does is it reduces the system from being a complicated quantum mechanical problem to a set of masses coupled by springs with well-defined spring constants. So that is a welcomed and large simplification, and it allows us to produce phonon dispersions. If we go one step further and we look at the cubic term in the near the minimum of the expansion, then we can derive a lifetime expression, which allows us to say how long lived are phonons in the material. And this is important because, again, we would like to know how long the lifetime of our phonons are so that we can assess our thermalization loss more thoroughly. One other important thing to note when you're dealing with nanostructures is that you end up having a lot of bands in the material as a result of the number of atoms present in the real space unit cell. So that can complicate your decay processes a little bit. You have a lot more zone center modes at high and low energies, which can couple strongly to electrons potentially. And to date, I have looked exclusively at these high energy modes as coupling to electrons. There are 2 decay processes still possible, one in which one high energy phonon goes to 2 lower energy phonons with equal and opposite momentum, and that is considered to be the largest energy loss mechanism. If this is inhibited, then other scattering processes can still occur, such as the one drawn here with these arrows, but these are considered to be quasi-elastic because one high energy phonon always remains in the system as a result of these 3 phonon processes. This red diagram here, all decay processes can go forward, and so this is considered to be a worse situation. Okay. So here's some results from some modeling work that has been done for FCC and quantum dot superlattices. And in both cases, we can derive a phonon band gap from the modeling which is large enough to inhibit first order phonon decay. And the reason why this happens is because there are some light, small features in the material which are able to resonate at high frequencies relative to the rest of the atoms, which are much heavier. And that produces these high energy bands, which are sort of split off from the rest of the bands, which are down here, and creates a phonon band gap which is large enough to inhibit this first order phonon decay. So that is how this comes about. So this is encouraging. This is a positive result. It's a highly constrained system, but at least there's some system which produces phonon band gaps for nanostructures, which is large enough to inhibit this decay mechanism. Also, we can derive phonon lifetimes, as I mentioned, from the cubic term of the anharmonic potential, of the interatomic potential, anharmonic term, and assess the lifetime of a phonon in a system where the band gap for phonons is not complete. There are states in the band gap which would allow for decay processes to go forward. And in this case, for a diamond quantum dot superlattice, that meaning that the quantum dots in the superlattice were in the diamond arrangement, a lifetime of 230 picoseconds was obtained from the simulation. Now, a typical phonon lifetime is about on the order of a picosecond or just a few picoseconds. So this is a 2 orders of magnitude increase in the amount of time that a phonon can live in the material. And so that's encouraging. That's quite a substantial increase. So just to summarize, some modeling work has been done and a few positive results were found where phonon lifetimes in nanostructures were quite large. But more generally, I'd just like to say the thermalization loss is a very important loss mechanism in a variety of solar cell configurations. Even multi-junction tandems, which are some of the most efficient solar cells that we have access to, have this thermalization loss mechanism to some degree. And the physics involved is very complicated and interesting. Adding phonons to your, as a sort of an extra degree of freedom to the system and having to analyze that makes for a very challenging project, very challenging thing to try to analyze, and it's been a pleasure to talk to you about it today. Thank you very much.
I'm sure Rob will take some questions.
Rob, thank you for the presentation.
Thank you.
So I was wondering, when you change your structure for phononic band gap engineering, won't the electronic band gap also change along with this? And when it changes, will it be for advantage for the solar cell?
That's a very good question, and it was something that I was thinking about last night while I was making this presentation. So the electronic band structure will also become backfolded inside of a nanostructured material. And is that an advantage or a disadvantage for hot carrier solar cells? I suppose that would depend somewhat critically on the energetics of the backfolding. So near the conduction band minimum, you would still expect that you would have this parabolic dependence for the electronic band structure. So that doesn't necessarily change the thermalization. However, if you have other minima which are now near to the conduction band minimum, which the electrons could potentially get promoted into, I suppose they could possibly stay there and see other minima from backfolding events. In terms of scattering with phonons, the phonon emission process can happen irrespective of the shape of the electronic band structure. So phonon emission would still go forward and likely at the same rate that it would have gone forward in the bulk material. Is that a good answer? Okay, thank you.
I've got a question here. I noticed an interesting feature in your phonon dispersion for the superlattice. I think it's for the FCC structure.
Yes.
You've got a high energy mode at the top.
Yes.
So can you explain why there is a high energy mode there?
So
Yeah.
you mean this slide?
Yeah, sure.
And you mean these modes up here?
Yeah.
Okay. So in the presentation I mentioned that these high energy modes are likely due to small light features in the material, small light features, clusters of atoms, which are able to oscillate at very high frequency relative to the heavier atoms in the system. So if you imagine that the spring constant, these force constants between these atoms are the same, then for restoring force of some amount, heavy atoms resonate at lower frequency than light atoms can. Light atoms are able to respond to that force a lot faster, so they can oscillate at higher frequencies. So the resonant frequencies are higher. Does that answer your question? That is what gives rise to these high energy bands in this dispersion.
And I asked, is that larger than the modes in the bulk material?
That is a very good question. Would that be larger than the modes in a bulk material? So for this kind of assessment, the nanostructure was modeled. It's a model material. It's not necessarily a one-to-one correlation with a bulk material. So the comparison may not be direct, but all of these simulations are kind of using similar parameters to indium nitride. So in the indium nitride band structure, there is a phonon band gap which is sufficient to inhibit first order phonon decay, 3 phonon decay. And in this system as well, there is a band gap of similar size. For configurations which do not have these small light features, this band gap is substantially smaller. So in nanostructured materials, if they are not engineered in a very careful way, you can end up with smaller band gaps, phonon band gaps, than you get in a bulk material.
Thank you very much.
Okay, thanks, Hong-Sen.
I had a question, if I may.
Of course.
You talked about the folding of the phonon modes and that creating a larger number of modes at zone center, and that those modes can actually be interacting with electrons. Could you comment on the degree to which they would interact as compared to unfolded modes in a non-nanostructure?
This is a very good question. Compared to non-folded modes in an unfolded band structure, I think the difference is rather dramatic. In non-folded modes in an unfolded band structure, we expect that there will be very, very little coupling between acoustic phonon modes and electrons, at least for Froelich type interactions. So there is long wavelength deformation potential scattering, which leads to phonon emission. This decay, well, energy transfer mechanism, I suppose, has not really been considered to be the dominant one in most of the materials, the binary compounds that we've looked at so far. In terms of energy loss, the up and down the phonon spectrum here, the energy versus momentum, the dispersion curve, this energy momentum relationship, the scale is linear. So if you scatter to a high energy phonon mode, you might be losing 3 times as much energy as if you scatter to a low energy phonon mode. So that, whether or not you want to call this an appreciable energy loss, if we can scatter to low energy phonon modes as well, is something that is an open question, how you want to define that. But yeah, scattering events between high energy phonon modes by Froelich interactions and low energy modes by deformation potential scattering, both of these things can exist in folded and unfolded structures. And to date, we've considered the Froelich interaction to be the dominant one, giving rise to phonons at zone center.
Okay.
Okay.
Thank you very much.
Thank you, Gavin.
And with that, I think we'll thank Rob again for the very interesting presentation on this interesting topic. Thank you.